Earlier, we used a simulation-based test to decide if seeing a graph alongside a description of a drug made people believe that the drug was more effective. Now we're going to look at the same scenario, except this time we're going to do a two-sample t-test. And our textbook organizes all the different hypothesis tests according to a 5-step process. So we're going to go through all 5 steps in this video. So the first thing that we want to do is to check the assumptions. And our book includes deciding whether this is the right type of test. So for a two-sample t-test, this is for a quantitative response variable observed in each of 2 groups. So we do have a quantitative response, the ratings of how effective people think the drug is, that's quantitative. And we're looking at 2 groups. So we have a categorical explanatory variable. It's binary, it has just the 2 categories, either text and graph or text only. We also need independent random samples that come either from random sampling or a randomized experiment. In this case, we do have a randomized experiment, so that's going to be supportive of cause and effect conclusions. And the last assumption is that we want an approximately normal population distribution for each group. So we don't have access to the population, obviously, but we could look at the sample to get a sense of the shape. This is mainly important for small sample sizes. So looking back at the histogram that we saw earlier, I wouldn't say there's any extreme skew here. Text only looks maybe skewed a little bit to the left. It looks like there's a couple of very low ratings. Text and graph looks pretty symmetrical, I would say. The other thing to consider is the sample size. So here we have sample sizes of 30 and 31. 30 is actually a pretty common cutoff for like how large your sample size needs to be before you can be more flexible about the shape. But just in general, I would say when you go to check these assumptions, just mention both the sample size and the shape. That way you can be sure that you're going to get full credit. So I'm going to point out that both of my sample sizes are larger than 30. And I am interested in both of them, not just one group. So both sample sizes are larger than 30. And there's no extreme skew. Maybe a little bit in each group, but nothing too crazy. So I'm going to say that this condition is also met. Our hypotheses, so we're going to put these in terms of the parameter. So the long run mean or the population mean, we represent that with mu. And we're looking at the difference in the 2 groups. So we had text and graph minus the mean for text only. The null hypothesis is that there's no difference. And the alternative, the question specifically asks whether including the graph would make people believe the drug was more effective. And so we're going to do a greater than sign here. That could be less than or not equal to, just depending on how the question was phrased. The third step is the test statistic, but before we can do that, we kind of need to think about the standard error. So the standard error describes how much we expect statistics to vary from one random sample to another. So in the simulation, we actually saw this directly, right? We did a bunch of different shuffles, we calculated the difference in means each time, and we could see that the sample statistics varied from one sample to another. And this is a standard deviation of the statistic, right? It's telling us how the statistics vary. So this number actually is a standard error. Notice how this is different from a standard deviation. A standard deviation is about what happens in the sample. How do individuals in the sample vary around the group mean? That's different from a standard error, which is telling you how the statistics vary around the parameter. So one way to get the standard error is to do it through simulation. Look at the spread of the null distribution. That's one option. But we can also predict this shuffle to shuffle variation without doing a simulation. We can use a formula for it. So I'm going to plug into this formula. I'm going to take my standard deviation for group 1, which was 1.177, and square that. Standard deviation squared is the variance. So I'm going to do the standard deviation squared divided by the group sample size, which was 30. And all of this is under the square root. Plus the standard deviation for the other group, 1.432, square that. Divided by the sample size is 31. and that comes out to be 0.335, which is pretty similar to what we got with the simulation. So the test statistic is different from a regular statistic. A regular statistic was like the difference in means, 0.7 or whatever it was. We don't really know when we just see a regular statistic whether it should be considered large or small. It's sort of hard to tell unless you're really familiar with the scale of the data. A test statistic helps by putting it on a common scale, or sometimes we say standardizing it. So we're going to consider the size of the statistic relative to the amount of variation in the data collection process, or you could say relative to the standard error. So I'm going to calculate my regular statistic first, which was the difference in the means, 6.833 minus 6.129. All of that together is my statistic. I'm going to subtract the null hypothesis value. So I'm looking here to see how far is my sample data from what I expected based on the null. And then I want to put that into standardized terms that I can understand, so I'm going to divide it by the standard error, 0.335. And that comes out to be 2.101. So to interpret that, I would say my statistic, which is the sample difference in means, is 2.101 standard errors, not standard deviations, standard errors above what we would have expected if the null hypothesis were true. So if there were really no difference, if adding a graph didn't actually make a difference, we're 2.1 standard errors above that. So this is sort of another way of saying, how consistent is my data with the null hypothesis? Is the null a good explanation for what's going on in my data? And when we're talking about quantitative data, this test statistic is called a t-statistic. So when all those assumptions are met, the ones that we checked in number 1, we can use a t-distribution to model the values of t that would occur if the null hypothesis were true. So in the previous video, we used a simulation to model the differences in means that would occur if the null hypothesis were true. But instead of calculating the difference in means as a way to summarize each simulated sample, we could calculate the t-statistic instead. So I'm just changing the statistic here. Now I have a distribution of t-statistics. Notice still centered at 0. We're still assuming that there's no difference between the groups. That's the basis of this simulation. And it's basically the same shape as it was before, but we're on a new scale. Now it goes basically from -3 to 3. That's what we would expect. And it's got this nice bell shape, and we can use a theory-based distribution to model that. So if we wanted to skip over the whole simulation process, we could use the t-distribution to tell us what values of t would occur if the null hypothesis were true. So I'm going to put in my t-statistic here, 2.101. And the count, that's doing a simulation, that's not really using theory. The theory-based p-value, the way they're calculating that is finding the t-statistic on the distribution and then shading under the curve. So we're finding our t-statistic. Here's 2.101 that we calculated earlier, and we're shading the area to the right. We're going to the right because this is a one-sided test, right? We had a greater than sign in the alternative hypothesis. And then this shaded area, this is the p-value, which came out to be 0.02. So I think this graph is helpful because it's really a nice illustration of how we interpret the p-value. Right? If we think about what this smooth curve is showing us, it's showing us the values of t that we would expect to get if the null hypothesis were actually true, right? So we're saying if the null hypothesis were true, what's the likelihood of getting t equals 2.101 or greater, right? That would be our p-value interpretation. So I think that's helpful for illustration, but probably in real life you're going to use JUMP for this. I'm going to go to Analyze Fit Y by X. So Fit Y by X is the appropriate choice when you have two variables, explanatory and response. So in this case, our response variable is the ratings, and our explanatory variable is the groups. And I'll click OK. And right now it just gives me the dots. It's actually pretty hard to see with this graph because we have a lot of repeated values in this data set, and it's sort of hard to tell which ones are occurring more frequently. Then I'll click the red arrow. It'll give me a lot of different options, but for now I'm just going to pick t-test, and it gives me all of this output. So here where it says difference, this is the difference in means, so like x bar 1 minus x bar 2, that 0.704 that we saw before. Where it says standard error of the difference, that's the standard error that we calculated earlier, so they're using that same formula. Here where it says t ratio, this is our test statistic or our t statistic. And then we have 3 different p-values, so we have to pick the appropriate one depending on what our alternative hypothesis was. So we had greater than in our alternative, so our p-value is 0.02. Notice that it gives us 2 different one-sided p-values. So this is greater than and less than. They add up to 1. It's always going to be that way. And then this one with the absolute value sign in it, this is the 2-sided p-value. So it'll give you all 3, and you'll pick the one that's appropriate for your data. By the way, I noticed that I was being a little bit inconsistent, so I had changed the labels at some point. So notice that this says yes minus no. So yes means yes, there's a graph. So this would be like text and graph minus text only. And that's actually backwards from how it comes up in JUMP with these other labels. And the reason is because JUMP puts things in order based on alphabetical order unless you tell it otherwise. So like right now, text only minus text and graph, notice that the difference is negative. It's the same number, but it's negative instead of positive. The t ratio is also negative. And if things were written in that order, we would have used a less than sign instead of a greater than sign. So all the same information is still there. You just want to be careful and make sure that you're interpreting it in the same way that JUMP is doing it. You can also tell JUMP what order you want things to go in. So I can right click here and choose column info and go down to column properties, value order. And this will allow me to switch them. So I'm just going to click reverse and click OK. And now let's try the same thing. Let's analyze fit y by x. And I'm going to do a t-test. And now that it's in the other order, I've got my positive numbers back again. So it's up to you whether you want to just like let JUMP put it in alphabetical order and go with it, or if you want to adjust it to the way that makes the most sense to you. Okay, so we've used JUMP to calculate the p-value. Then the conclusion, that's the same as it would be for a simulation-based test. The smaller the p-value, the stronger your evidence against the null and in support of the alternative. So in this case, we would say that we have strong evidence to suggest, and I'm just going to sort of keep it short in how I phrase the alternative here, to suggest that graphs do make a difference. To say that looking at a graph makes people believe that the drug is more effective.